The next water pumping problems we're going to look at involve tanks where the cross section is not always the same size. And so the first example I want to do is something like this where we have a conical tank. Now this conical tank, its radius is 4 feet, which I don't know if that really printed very well. Its radius is 4 feet and its height is 10 feet. And we want to come up with the amount of work required to pump all the water out. So like before, I'm going to put in I'm going to draw in a slice. I'm going to do it in blue since it's supposed to be water. So here is a slice of water. And I'll make it slightly three-dimensional looking. And I'll even color it in since it's supposed to be water. I'll make it blue. All right. So we've got to work out, like before, we've got to work out the weight of that slice of water, and we've got to work out its how far up it has to get pumped and everything. So first up, here's what I'm going to do. This is the radius of this thing, and this right here, it would make sense to call this height, but I'm gonna change that in a second because the thickness of this I'm going to call, as before, I'm going to call that dx. And so if that's a tiny change in x, then I want to call that, instead of calling it h, I want to call that x as well. So let's see. Let's rewrite that as x. And we know that the volume of the slice is going to depend on r. So volume, let me go ahead and write this up here, slice. The volume is going to be pi times r squared times dx. And the weight is going to be 62.5 pi r squared dx. Why 62.5? 62.5 is the mass, or it's the weight density of water in pounds. Let me write that over here. 62.5 is the density of water in pounds per cubic foot. So that's where this number just kind of pops out of nowhere from. So basically, use 62.5 if you're dealing with feet, and we'd use 9,800 instead of this if we were dealing with meters and kilograms. All right, so that's the weight of the slice. The problem is we've got an r in there and we've got an x. So let's replace this r with something involving x. So get rid of r. Now the way we'll do that is by looking at over here at some similar triangles. I'm going to redraw it over here. Let's see, this is 4, this is r, this is x, this whole thing here is 10. So what you can do is you can say r over x is equal to, see, r over x equals 4 over 10. Or let's see, 10r equals 4x. We're trying to solve this out for r. So you get r is 4/10 of x. Or, you know, we're already dealing with decimals. R is equal to 0.4x. All right, so that gives me that the weight is 62.5 pi times 0.4 r quantity squared dx. And that's the thing that we need to integrate. So the total work, or wait, before we do the total work, let's work that out. 0.4 squared is going to be 0.16. 62.5 times 0.4 squared. Oh, that's convenient. But when you multiply 62.5 and 0.4 squared together, you wind up with getting 10. So you get 10 pi r squared dx. I was prepared for that to be ugly, but it turned out really nicely. All right, so that's our that is our weight of the slice. So how far up does that slice have to be moved? Well, let's go back up to our diagram. What is that distance right there? Well, if the total distance from bottom to top is 10, and that's x, this is going to be 10 minus x. So that means our total work is integral of 10 pi r squared, wait, this r up here. That shouldn't be an r, that should be an x. And same thing above, that should be an x. Because basically this r gets replaced with 0.4x. Okay, so we're good to go there. Our overall integral then is going to be integral of 10 pi x squared times 10 minus x dx. So we've got force and then in here distance. And what are the endpoints? Well, the lowest value of x is 10 and the highest is 0. Or maybe I said that backward, but anyway, it's going to be the integral from 0 to 10 of this. Now, that's an easy integral to do, but I'm just going to do it with decimals. Let's see, integral of 10, integral from 0 to 10, do that again, integral from 0 to 10 of 10 pi x squared times 10 minus x dx. And it gives me that number right there. I'm adding a voiceover in here to correct a little mistake I made on this. The number there is correct, but since this was given to us in pounds and feet, that should not be a J there for joules. It should be pound feet.